Hello, good morning. Uh, Welcome to for um, the second ever class on introduction, importance, and history of plant breeding with a special reference to vegetable breeding. We have discussed yesterday, in the previous class, about the how important the vegetable crops breeding is and what are milestones happened in the uh, breeding in general, and also some specific examples with the vegetable crops and the efforts and whatever the achievements also in the um, history of vegetable breeding in India. Now, just to give some more introductory background on this vegetable breeding, just to discuss today, continuation that factors limiting the genetic improvement of croplands. So before we start, what all the things which are really hindering the progress of this breeding? Uh, First and foremost thing, always we should remember and also realize there is a narrow genetic base, meaning the limited number of genes are being extensively used and they are available. Few genes are there and it is being used extensively. So we have examples like Norin dwarfing gene in wheat. It is used extensively. First, of course, it was Japanese variety, that gene Norin. That particular gene was used, and worldwide this is exploited. Single gene, one gene, whatever they found, it was exploited world over. And time of EV cytoplasma, majority of wheat, which is being used extensively by Borlaug and subsequently many plant breeders. Then OPEC2 and T cytoplasma of maize, or DGO gene in rice for dwarfing, Milo, that is a majority in sorghum, um, Tipton majority in fulminate, and of course, of late, that BT gene, or it is being used in majority of the many of the vegetable crops, including that cotton, the BT gene, which is used irrespective of the croplands. So what does it mean? That we have very few genes known, identified, and they are being used extensively. That is one of the drawback or the limiting factor in crop breeding. So if you have got more number of genes, you can really use. What is the advantage of having more genes? There may be the adaptability of that gene. If you are some one particular gene is not found suited for using that incorporated variety in a particular zone, that means you don't have the alternative for that. So always, if you have got more number of genes, for a particular character, identify different sources. What else? The genetic base overall. It is not just the one gene we are specific. The genetic base, if it is wide rather than narrow, it is going to be advantageous. And most of the cases, many of the cases, we are limited by this, the narrow genetic base in the croplands. So that is one. And then second is absence of suitable plant type. That is idiotype. What is that ideal plant you want to have as a variety? How that particular variety should be? Many a times we are not able to, the decide and judge what really we want to have. Always it's a imaginary, and only the objectives you can set for developing a variety. If you don't have that, so many a times we lack that imagination, lack of this idiotype, which is very ideal type. You have to define each character, and then you can have the variety, what kind of variety you want to have. So there should be a balance increase in the source and sink, uh, and of course the sink alone. That means where the carbohydrates are produced and where it is being stored, which you are realizing it as a yield. That's important. It's not just you want to have a plant with the high yield without any support from the photosynthetic aperture. If you have got sufficient area for the photosynthesis, then only you can expect the higher yield. That means each and every character of the plant you have to define. That is your radio type. You are imagining your variety should be like that. So this is important. Balance increase in the source and sink. It's not just only sink alone. It should be both source where it is produced, the carbon is produced, and where it's always you think about the sink yield only. You are having absolute high yield. But you can't get a high yield just by one single stem and the dwarf plant without having any branches. You cannot expect that. That means the supporting system to get that yield in the plant, like the more branches, maybe the taller, maybe the more leaf number, leaf area, more production branches. So all that you have to keep in your radio type. That is, you have to define plant how your variety should be. So developing leaf is a sink, and later it becomes the source. Many times, the first uh, uh, phase of the leaf growth, if you take, it's not going to give you the photosynthesis supply being supplied to the other part. It is going to be the sink at the time of development. When it develops, then it becomes a source. So within source also you have got this complexity. So if you think that the small leaf, it's going to consume the photosynthesis. Now once it grows, then it becomes the source. So developing leaf is a sink, and later it becomes the source. Should remember, based on that you have to, right? You have to develop this idiotype for each and every crop. You should have every location. This is the ideal type of plant which you want to see it as a variety that you define. That is lacking. Then, of course, the next the problem. Those are the inherent problems can be there, or external factors like unpredictable genotype environment interaction. So you cannot predict, how this genotype is going to interact with the new type of environment, or maybe the season, maybe the location. It's unpredictable, right? You are just guessing it. That's one of the hindrance in the crop breeding. That is G into E interaction, that buffering effects of environment. You are seeing it, how this genotype is going to behave with change in the environment. It's not predictable. That's the hindrance. You cannot have the kind of genotype you can decide that, oh, if I develop this kind of genotype, that will perform best. No, nothing like that. Unless till you assess it, you will not be knowing it. So that is unpredictable gene to E interaction. Cannot predict it. And then the next drawback is the small population size and indiscriminate experimental designs. Many times plant breeders are helpless, that they don't have the sufficient source. Very small area, because you need a lot of labor, other sources, land also maybe a limited things, because you have got so many breeding programs, so many crops are there. You may not give that much, the area for raising the ewes. And also, what will happen? They are not. That is one of the drawback. Small population only want to make the selection. No, if bigger the population size, the chances of having superior genotype is more. So then the indiscriminate experimental designs. Many times you don't follow the right kind of design. Maybe because you are helpless. Maybe because you do not know. Both the reasons are there, whether this particular experimental design you have to follow. For example, I tell you, you are raising some 100, 200 genotypes for evaluation. You are just simply putting it in RBD, because a large area, your assumptions for RBD is not met out, because what you assume that one block, there is a homogeneity, there is uniformity in the entire replication one. That itself is not true, because this area is big. You don't expect the soil being uniform. So instead of that, you may have to follow the augmented design or something like that. It's just example I have given. Like many a times, either you are helpless, or you do not know. So the indiscriminate experimental designs being used is one of the small size of the F2 and F3 families grown and retained, because you have got so many other breeding programs handling, many other crops are there. Then it is being limited. The number of plants for F2 you are limiting, because it starts segregating means more genotypes, more permutation combinations of genes, so that more number of genotypes segregating in F2 and F3 you can get. And if you reduce the size, some of the very rare things you are going to miss. The one single, I mean, the two genes controlled character, if you want to look at, you need to have minimum 64 plants. Then only out of 64, only one plant you can get double recessive gene. So by chance I mean, it's going to miss. 1 in 64, there is every chance of missing that plant. So you have to have huge population. Then only the chances of getting those rare genotypes. So your small population size is going to hinder the plant breeding program achievements. Lack of sensitive design, as I said, if you do not apply your mind, or you don't know, or you are helpless, everything is going to be, the negative factors. So RBD and large population and BIBD, one more thing can be there. Hardly, plant breeders think about this BIBD. What is the importance of that? The most of the time it's limited to the elements trial, that is nutrition trials only. So maybe some modifications you have to look at, so that can help. So these are all, the whatever we have discussed, it is like, there's a narrow genetic base, as such it is there, are the absence of the suitable type that objective to set, or unpredictable genotype into environment effect, and the small population size. All these are, the external factors. Now the inherent genetic barriers are there. That means within a crop, although you have got all other drawbacks you have taken care of, but within a plant you have got some of the problems that is hindering the pace of this plant breeding. First one is, we can list plenty are there. Few examples, I mean, few we can list here. Negative genetic association. So that is, for example, one example we can take it in tomato. Jointless gene, J gene in tomato, is associated with the fruit cracking and the low yield. Of course, that is one example. Meaning, what is that? You want for mechanical harvesting easy removal of the fruits. You want easiness, you want, but that gene is unfortunately associated with fruit cracking. So this negative association. One, you want to have the jointless gene plus the fruit free from cracking. But this negative association, you have to break it. You have to go for specialized designs, and that is going to take your more resources. So that's going to be one of the drawback or inherent genetic barriers for cropping. And many of the cases, like, the low yield and high protein in case of legume vegetables. Whenever you are looking for the higher yield varieties, genotypes, you are going to lose the protein content of that variety. So this is a negative association between these two characters. Like that, you have plenty of examples of negative genetic association. For example, many you can get one character is good, favorable for you, the other character, like, disease resistance may be being associated with the small fruit size, bitter fruit. So many undesirable things it can be associated. That itself is the hindrance for crop breeding, the negative genetic association. Then limited fixable component and low heritability. So fixable component is additive variance. You are sure. The non-additive means you have to go for a specialized breeding methods like heterosis and all, or recurrent selection. But if you have got fixable additive component is there, you develop a pure line variety. That solves your problem, because pure line variety seed production is easier. Just isolation is sufficient. It's not like, the hybrids or some other products that seed production itself is a problem. So in that sense, limited fixable component and low heritability. That's additive component. If it is less in your population, then you are bound to look for something else. and low heritability for many of the characters. Although, what is that heritability? Whatever the variation you are seeing by your visual observation is not being carried. It's not heritable. That means you make a selection based on your visual observations. Next generation, whatever seeds you raise in the next season, that will not be seen because heritability is low. So when heritability is low, you won't get. The success of plant breeding it depends very much on the low, high heritability. High heritable only your selection is a sense. It makes sense. Otherwise, there is no point in selecting good plants. Whatever you're saying. A good plant, if you say now, if you raise it for the next generation or the next season, it should be good plant only, high yielder only. But if heritability is low, it will not help. So that's one of the the drawback. So additive genetic variance and is rapidly exhausted. Whatever available additive variance is there, a few cycles, you are going to use that, and subsequently you don't have sufficient additive component in that crop variability. Then the correlated response. Correlated response is also one of the inherent genetic barrier. That the negative genetic association of small fruit size and the number of fruits. If you look at specifically like tomato or even in capsicum, the plant, if you choose with having more number of fruits, it is always going to have small fruits, small size fruits. If you want to have big size fruits, fruit number is going to go down. That means both these are required for us to increase the yield. But there is a correlated response, that negative genetic association between the two desirable characters, small fruit size and number of fruits. So that itself is going to be one of the inherent genetic barrier. Then maternal effects. So maternal effects means certain the characters are controlled by the cytoplasm, and that has to be inherited only from the female parent. So it's not simple designs. Whatever you make, you will get it. If that character is, invariably you have to use the female parent only for the next. That means simple designs to study genetic variation will not be useful for the characters which are controlled by maternal, that means cytoplasma. So that general, whatever these principles are there, majority of the breeding schemes, they revolve around the nucleic genes. That means both parents are contributing. Whereas here, it's only female is contributing, maternal effects. Simple designs are not going to be useful. So that itself is one of the inherent genetic barrier for crop improvement. Of course, that maternal effects we make use for F1 seed production, that is a different issue. Then, the linkage disequilibrium. So it occurs due to the extreme proximity of the genes on the chromosome. So you don't expect any further improvement. This linkage disequilibrium, if it is observed, most of the times you are getting into extreme proximity of the genes on the chromosome, little or no response to improvement by selection in that case. So they are proximity, they are near. It's just like, the recombinations you want to have, and it is not happening because of the close proximity of those genes. So that itself is your, the reducing pace of this crop improvement. Then genetic asymmetry arising due to the directional dominance and directional gene frequency in the population causes the lack of response to the selection. It's population improvement for the multiple gene controlled characters, specifically for the yield. After some time, there is no response for the improvement for selection for the yield. It's because of genetic asymmetry. So it is directional dominance is there only, and then the gene frequency is only one side. Whatever it is there, you have exploited, and subsequently you don't get the further response. Then non-realization of hybrid vigor. Many times, mutual cancellation, although there is hybrid vigor is there, mutual cancellation of the components of heterosis. For example, heterosis for fruit number, you got it. More fruits you have got. but fruit size is negative, then yes, both mutually it is cancelling and you don't get any heterosis for the yield. Like that, non-realization of this hybrid vigor, although for one character is there, or one character is negative. And then inability to exploit hybrid vigor. So that is, the many of the crops like legumes, although sometimes you get the hybrid vigor, but you cannot exploit it because of the seed production system. You cannot hand emasculate. You don't have good system of male sterility, or although you have got male sterility, that natural cross pollination is not there. The F1 seed yield is going to be low. So you maybe the handicap with you cannot have this good F1 seed production system, although the heterosis is existing. That is one of the inherent genetic barrier. Then, of course, desirable characters controlled by polygenic recessive genes. This is one of the very important. Always to improve the character which is controlled by polygen itself is a complex. And in addition to that, if it is recessive, polygenic recessive, still it becomes more slow, non-responsive. It is difficult to accumulate. The background breeding for dominant gene and recessive gene there is a big difference, right? The procedure, additional things, additional steps you have to involve. So, single gene itself, you are getting into complication. If it is polygenic recessive, it is further complicated. So those characters are desirable, but controlled by polygenic recessive, always the pace of improvement, crop improvement is less slow. So list whatever we have listed, this inherent, genetic bottlenecks is far from complete. Many are there. If only few have taken example. So bear that in mind, and they have to always fighting for solving some of the problems in a specific crop. Finally, Allard and Hansi listed the following reasons for slow progress. There are genetic barriers, but what these scientists have postulate, brought out where is the bottleneck, where is the main reason for slow progress in plant breeding. One is the inadequate variability, right? Lack of systematic sampling of total range of variability. That sampling technique itself is very faulty. Plant breeder is not good enough his intelligence or his ways, approaches, his knowledge. Then, of course, small population, you are hindered. You don't have sufficient area for your breeding programs. Plenty of tasks are there. Then high selection pressure. Most of the time, suddenly we want to get what is that? I tell you, for example, this high selection pressure meaning, for example, in this class of like 100, I want to select best one student. But I tell you, best one student by chance, but that time, whatever the selection pressure is there, environment is there, there is a very next man who is equally competent. By that, by chance, he has not done well during that particular, the exam because of some other reasons. Otherwise, he is equally good. So that means always your selection pressure, instead of selecting one man, you should select some top 5. That means they're all 5 equally competent, and how they do it in different conditions, it's one can do better than the other always. The same thing is there in plants also. The top best plant you are selecting, suddenly that may not do it well because it's being influenced by environment, and your selection pressure should not be very high. What does it mean? The plants are there. Out of that, you should select 10 plants, not that 1 or 2. Select 10 plants. That means those 10 best plants can do well because you have taken care that the environmental factor in interference, G2 interaction of the start 10 plants, or at least 1 or few can be better. So that's why your selection pressure always should not be very high. You're bound to lose very precious genotype by this, the high selection pressure. Then improper understanding the principles and procedure employed by the breeder. Many times I told you, if they are not good, they're geneticists, or rather they don't have the sufficient knowledge of the genetics, they cannot be the good plant breeders. They may be lucky, sometimes they can succeed, but improper understanding the principles and the procedures applied, why they are doing this, what is the basis for that. If they don't know, that means they it becomes a failure, right? You will end up with no results, no improvement in plant breeding. So, lack of imagination, that is your ED type. Vision, what you need, efficiency, but always you should try to save the resources. Don't always keep on, blaming that I have been not given this facility. That's why I'm not able to do it. No, the efficiency is very important within the available. One side we say there is lack. Yes, understand. Yes, there is a limited resources, but you have to be efficient to perform well under such limited resource facilities. So there is vision and efficiency. So lack of imagination, lack of vision, and lack of efficiency in incorporating existing variability into improved varieties is the main reason for slow progress rather than lack of variability. Borlaug said it. You say there is lack of variability, I understand, but whatever available variability is there, by and large, entire globe, plant breeders involved and the account it's taken into account. It is lack of imagination, lack of vision, lack of efficiency in incorporating the existing variability into the improved varieties is the main reason for slow progress of this crop improvement rather than lack of variability. So always don't blame. Okay, so you have to improve whatever possible in your hand. You have to be, the good enough to handle. Then only the pace of the cropping can be increased. So that is, the bottlenecks and how the plant breeders should be, then how they can handle it. Now the evolutionary trends and development of cultivars. This is very important because unless you know the evolution of that particular plant, you will not be, able to handle the program efficiently. What has happened there? What kind of, the genetics is there? How the genotypes have evolved? How the species relation has changed? How the species, the interaction is there as far as the reproduction of pollen, the compatibility is concerned. So that's all brought in the course of evolution. What are the evolutionary trends? It is important to know, and development of cultivars. So evolution is a slow process, whereas development of cultivars is an extended form of evolution. It is a faster process. Remember, same. If you know that, then only you will be efficient. Otherwise, you will be poor plant breeder. So you should know that evolutionary trends. Somewhere the plant breeding is merely a continuation of the natural evolution of the crop plant species, changing its course in the direction of greater use to mankind. Knowledge of evolution is essential for future course of crop improvement. You should always not simply straight away get into the crop improvement. You should know the entire history of it, how that crop plant has particular species has evolved. The evolution is important for the plant breeder to know. Then only it be a successful plant breeder. They will be efficient in developing varieties. Evolution, it refers to origin of new species or organisms through a long, drawn, and a continuous process. It is formation of the new species. It's not immediately going to happen. It's a very long process and a continuous long process. So that is referred as evolution. So initial steps, it is in the course of evolution, it is always creation of variability. Some changes you have to bring it. Then once the variability is created, next is the selection, fitness. That means survival of the fittest. But natural selection, some environmental, like sudden increase in the temperature or rainfall or whatever, some change in the environment. That will put the selection pressures. That means the genotypes which are not fit will disappear. The first, variability has to be created. Without variability, there is no crop improvement. And the same thing in the evolution also. Evolution means first the species throws the variation and then the selection. So the different types will come into survive. So extreme type, always remember here in course of evolution, extreme types are eliminated. Very good will also eliminate, very bad is also eliminated, and intermediate types are favored. and they establish as a subspecies, and they are not committed to a separate evolutionary path as are the species. Their reproduction is in isolation and no gene flow between the species. Now, the intermediate types will get separated, and there is a barrier. Now they are being raised in isolation, and there is no exchange of the genes. Gene flow will not be there, meaning there is no compatibility between them, and they will establish themselves as a species normally, right? So this is going to be the continuous process. So remember here, extreme types are eliminated, intermediate types are favored. I tell you one example here. The previous one, the census, when once the survey they did it, and they said 80% of the dropouts, right? 80% of the dropouts are having the high IQ. So they don't feel like sitting in the classroom. They are very intelligent. Their IQ is very high. They don't adjust. They 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 go out. They go out high school. They maybe many of them are becoming criminals, right? So that means this very good you said, they also will not survive, and very poor, of course, you will not be in the competition. But why that very good you are saying, and but still they are not in the mainstream? This is the reason. So this is going to happen in plants also. Uh, that may be associated with some negative things. What the parameter you are taking, it's good. Top you are saying, it may be associated with some other negative things, and they'll get eliminated. So intermediate types means there may be majority of things are intermediate genes. I mean, the genes which are having the potentiality to be them intermediates, they will survive, they will exist, they will sustain and become a new species. So evolutionary forces and crop evolution, if you look at, there are two important forces here, revolutionary forces. That is, and the what revolution means changes. First, you have to create variability. There are two important mechanisms in the plant system which brings the variation. One is the mutation, sudden change in the heritable traits, I mean the genes. So mutation, it's going to happen whatever way, whatever. And then the recombination. It's not only that, the changes of genotypes to happen, combination of genes, right? Recombination after hybridization in sexual organisms. Sexual reproduction itself is one of the forces to create variability. If it is homozygous, self-pollinated, don't create the variability. The cross-pollinated crops, they can sustain because of that, the hybridization, natural hybridization, panmixia, open pollination. Then the more variation is created, and that will have the answer for this changing environment. It can survive through different types of genotypes. They can have an answer for change in the environment or selection pressure. So evolutionary forces are mutation and recombination after hybridization in sexual organisms. Then, of course, asexually propagated mutation always happens. That's of course. But sexually propagated, both mutation also can happen, and the sexual reproduction and the mutation, of course, the sudden change, new genotypes you can get it. But here it is the combination of the gene can give you the new genotype. Then the second most important force is evolution force. It's a conservative force. So conservative means it will not give the new things, but it will try to preserve those whatever new things have come. And the things are there, the genes are there. Conservative forces which preserve certain constellation of the genes over a large number of generations. They will preserve those combination of genes for a large number of generations. So good, whatever it is said once, they'll be preserved for a longer period of time, rather than creating a new one. So that is conservative force. It is for example, like selection pressure, natural human selection and genetic drift, whatever. What will happen? The other types are going off, and the remaining things, whatever are there, they are being conserved. One selection pressure is there means all those genes which are favorable for high temperature or some, prevailed, or some particular disease came, and the resistant genotypes only will be preserved, others will disappear. or high temperature tolerant genotypes will preserve. I mean, it will sustain. Others will wait. Just a minute. Hello, Adrian. Yes, sir. Uh, so the different types will come into survive. So extreme type, always remember here in course of evolution, extreme types are eliminated. Very good will also eliminate, very bad is also eliminated, and intermediate types are favored. And they establish as a subspecies, and they are not committed to a separate evolutionary path as are the species. Their reproduction is in isolation and no gene flow between the species. Now, the intermediate types will get separated, and there is a barrier. Now they are being raised in isolation, and there is no exchange of the genes. Gene flow will not be there, meaning there is no compatibility between them, and they will establish themselves as a species normally, right? So this is going to be the continuous process. So remember here, extreme types are eliminated, intermediate types are favored. I tell you one example here. The previous one, census, when once the survey they did it, and they say 80% of the dropouts, right? 80% of the dropouts are having the high IQ. So they don't feel like sitting in the classroom. They are very intelligent. Their IQ is very high. They don't adjust. They, they they go out. They go out high school. They maybe many of them are becoming criminals, right? So that means this very good you said, they also will not survive. And very poor, of course, you will not be in the competition. But why that very good you are saying, and but still they are not in the mainstream? This is the reason. So this is going to happen in plants also. Uh, that may be associated with some negative things. What the parameter you are taking, it's good. Top you are saying, it may be associated with some other negative things, and they'll get eliminated. So intermediate types means there may be majority of things are intermediate genes. I mean, the genes which are having that potentiality to be them intermediates, they will survive, they will exist, they will sustain and become a new species. So evolutionary forces and crop evolution, if you look at, there are two important forces here, revolutionary forces. That is, and the what revolution means changes. First, you have to create variability. There are two important mechanisms in the plant system which brings the variation. One is the mutation, sudden change in the heritable traits, I mean the genes. So mutation, it's going to happen whatever way, whatever. And then the recombination, it's not only that, the changes of genotypes to happen, combination of genes, right? Recombination after hybridization in sexual organisms. Sexual reproduction itself is one of the forces to create variability. If it is homozygous, self-pollinated, don't create the variability. The cross-pollinated crops, they can sustain because of that, the hybridization, natural hybridization, panmixia, open pollination. Then the more variation is created, and that will have the answer for this changing environment. It can survive through different types of genotypes. They can have an answer for change in the environment or selection pressure. So revolutionary forces are mutation and recombination after hybridization in sexual organisms. Then, of course, asexually propagated mutation always happens. That's of course. But sexually propagated, both mutation also can happen, and the sexual reproduction and the mutation, of course, the sudden some change, new genotypes you can get it. But here it is the combination of the gene can give you the new genotype. Then the second most important force is revolution force. It's a conservative force. So conservative means it will not give the new things, but it will try to preserve those whatever new things have come. And the things are there, the genes are there. Conservative forces which preserve certain constellation of the genes over a large number of genotypes to happen, combination of genes, right? Recombination after hybridization in sexual organisms. Sexual reproduction itself is one of the forces to create variability. If it is homozygous, self-pollinated, don't create the variability. The cross-pollinated crops, they can sustain because of that, the hybridation, natural hybridation, panmixia, open pollination. Then the more variation is created, and that will have the answer for this changing environment. It can survive through different types of genotypes. They can have an answer for change in the environment or selection pressure. So evolutionary forces are mutation and recombination after hybridization in sexual organisms. Then, of course, now asexually propagated mutation always happen. That's of course. But sexually propagated, both mutation also can happen, and the sexual reproduction and the mutation, of course, the sudden some change, new genotypes you can get it. But here it is the combination of the gene can give you the new genotype. Then the second most important force is evolution force. It's a conservative force. So conservative means it will not give the new things, but it will try to preserve those whatever new things have come. And the things are there, the genes are there. Conservative forces which preserve certain constellation of the genes over a large number of generations. They will preserve those combination of genes for a large number of generations. So good, whatever it is said once, they will be preserved for a longer period of time, rather than creating a new one. So that is conservative force. Uh, it is for example, like selection pressure, natural human selection and genetic drift, whatever. What will happen? The other types are going off, and the remaining things, whatever are there, they are being conserved. One selection pressure is there means all those genes which are favorable for high temperature or some, that prevailed, or some particular disease came, and the resistant genotypes only will be preserved, others will disappear. Or high temperature tolerant genotypes will preserve, I mean, it will sustain, others will wait, just a minute. Hello, ಹೇಳ್ರಿ Yes, sir. ಹಾ ಹ್ಞೂ. ಹ್ಮ್ 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 ಮತ್ತ ಅದ್ ಮಾಡ್ಬೇಕಲ್ರಿ ಮತ್ತ ಅವ್ರು. ಹ್ಮ್ ಓಕೆ. ಹ್ಮ್ ಹ್ಮ್ ಹಾ ಹೇಳ್ರಿ. ಈಗ ಕಾಯಿಲ್ ಹೋಗೋದಿಲ್ಲ ಅಂತ ಹೇಳಿ ಮೊದ್ಲೇ ಗೊತ್ತಾಗೋದಿಲ್ಲ ನಿಮ್ಗೆ? ಹಾ ಇವಾಗ ಹ್ಮ್. ಹಾ 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 ಇದು ಎಷ್ಟ್ ಹಳಿದೈತ್ರಿ? ಅದು ಬಾಳ ಹಳಿದೈತಾ? ಹ್ಮ್. ಹ್ಮ್ 5 ವರ್ಷಿಗೆಲ್ಲ ಲೀಕೇಜ್ ಯಾಕೆ ಅಂದ್ರೆ ಏನ್ ಪೈಪ್ ಎಲ್ಲ ಇದಾಗಿರುತ್ತಾ? ಹ್ಮ್ 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 ಅದು ಎಷ್ಟಾಗ್ತದ್ರಿ? ಕಾಯಿಲ್ ಎಷ್ಟಾಗ್ತತೆ? ಹೌದಾ? ಓಹೋ. ಅಲ್ರಿ ಇಷ್ಟ ಎಲ್ಲ ಈಗ 10-15 ವರ್ಷ ಉಳ್ಕೊಂಡಿದಾವ, ಇದು ಹೆಂಗ್ ಇಷ್ಟು ಬೇಗ ಹೋಗ್ತಾವ ಇವು? ಅದು ಯಾವ್ದದ ಕಂಪನಿ ಯಾವ್ದದ ಅದು? ಹೌದಾ? ಮತ್ ಬ್ಲೂ ಸ್ಟಾರ್ ಎಲ್ಲ ಅವ್ರ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಅಲ್ಲ? ಹ್ಮ್ 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 ಸರಿ ಆಯ್ತು ತಗೊಳ್ರಿ ಮತ್ತೆ. ಹಾ ಆಯ್ತು ಹಾ ಓಕೆ. ಆಯ್ತು ತಗೊಳ್ರಿ, ಕೊಡೋಣ, ಕೊಡ್ರಿ ಅವ್ರಿಗೆ. ಹಾ ಅದೇ ಸರ್. ಈಗ ಅದೇನು ಅದೆಲ್ಲ ಆಗೋದಿಲ್ಲ ಇವ್ರದ್ದು. ಸುಮ್ಮನೆ ಅಲ್ಲಿ ಲೋಕೇಶ್ ಅವ್ರ ಇದ್ರೊಳಗೆ ನಾನು ಟೇಬಲ್ ಹಾಕ್ಬಿಡ್ರಿ, ಅಲ್ಲೇ ಇದ್ಬಿಡ್ತೀನಿ. ಅದು ಸರಿ ಆಗೋದಿಲ್ಲ. ಹಾ ಹಾ ಅದೇನ್ ಇದಾಗೋದಿಲ್ಲ, ಅವ್ರಿಗೂ ಹೇಳಿದೀನಿ. ಯಾಕಂದ್ರೆ ಇದು ಅಷ್ಟೆಲ್ಲ ಇವ್ರು ಕಾಸ್ಟ್ಲಿ ಇವ್ರೇನ್, ಯಾಕಂದ್ರೆ ಇಷ್ಟಕ್ಕೆ ಸಣ್ಣದಕ್ಕೆ ಇದು ಮಾಡ್ತಾ ಇದಾರೆ ಇವ್ರು. ಇದಕ್ಕೆಲ್ಲ ಹೆಲ್ಪ್ ಮಾಡ್ತಾರೆ ಇವ್ರು. ಹಾ ಹಾ ಸರಿ ಓಕೆ. So that is the selection pressure, natural. And then the genotype factors favor the homogeneity among the individuals. The limited number of chromosomes are there, and there is a linkage between the loci that will preserve the same thing, whatever it is there. And that is genetic factors, right? Fewer chromosomes, limited number of chromosomes means, or the changes, that species is going to preserve the same thing for larger number of generations. So the linkage is also going to help to preserve the same genes for large number of genotypes. I mean the generations time. Then the phenotypic factors conserve the variability, devices favoring the inbreeding, sterility mechanisms, self-incompatibility, mating discrimination, everything is there. Yeah, we are discussing about the conservative forces. That is, it preserves the certain group of genes for a large number of generations. Selection pressure, genotypic factors, and then the phenotypic factors conserve variability. Here to understand this, that there is the, for example, the sterility. If you say it is against, no, it will not. It will not allow for the self-pollination. In the conservation means it's most of the time self-pollination is going to help you to conserve that. Those cross-pollination means going to change. So inbreeding is, yes, inbreeding whenever the devices which favors the inbreeding only conserve. Whereas sterility mechanisms, that is not, you are not going to have the inbreeding, or self-incompatibility is also going to avoid this inbreeding. That means you are not going to conserve. It's again going for the creation or change of the variability. Mating discriminations are also there. There are plenty of the types of mating discriminations. I tell you, mm, like uh, mm, assortative mating and disassortative mating. It is said many times. You say uh, preserve certain constellation of genes. The most of the time. To speak about this assortative mating design, you can see even in the human beings also, the intelligent people, marrying intelligent, I mean, intelligent boy marrying intelligent girl. It is again going to be, the conserving that intelligence. That's like, the conservative force. Whereas the revolutionary force here, if you take this assortative mating, or like, the in America, uh, the whites marry the blacks. The blacks are always good, tall, stature, good sportsman, and you are going to get a good sports progenies. That is the kind of the revolutionary forces you can say. So ultimately, I tell you, the evolution is the balance between the revolutionary and conservative forces. Both are required, both are important. One is to create variation. Second is to, once it is variation is created, to make selection that good things are there, they will be preserved for a long period, a longer number of, I mean, larger number of generations, and that will result into a new species. So that is, the evolution, and you are going to create a species. So creation of species, if you just look at here, mutation and ploidy breeding give new species at a single stroke. Big change you can expect. Huh? Whereas uh, this genetic drift and selection and hybridization followed by recombination, which alters the gene frequency of a population, are slow process. It will not happen suddenly. The results into variability, but not as a new species. This is within a species variation you can create. Whereas mutation, big change, or polyploidy breeding, you can say, uh, ploidy level, if there is a change by some means, this chromosomal aberrations and the meiosis and the zygote form of fertilization, that will lead to a new species totally different. You may get a single stroke, you get a new species. Whereas genetic drift, selection, hybridization, recombination, slow change in the gene frequency, and it's going to be a slow process, results to variability within a species, but not as a new species. So pattern and source of genetic variation can be at a two level. Macroevolutionary relationship, gene exchange is difficult between the species and genera, right? Whereas microevolutionary relationship varies with the species. There is a free, the access of genes. That means the free flow of genes. They are cross-compatible, meaning, right? Whereas macroevolutionary separation, right? Gene exchange is difficult between the species. You take genera, you cannot cross, right? So within a species, there will be, for example, within a species also you can have some variations. I mean, the like cross-pollinated crops and self-pollinated crops. So that source, that will result into genetic variation, right? If it is random mating, cross-pollinated, variation is created. Self-pollinated, close, right? No variation created, but it will good things will be preserved for longer time, right? So very top level of evolution, if you say that reaches the dead end, that is self-pollinated. That means earlier it was cross-pollinated, and next it has given rise to a self-pollinated. Self-pollinated crops are highly evolved, you can say, from hot pepper, right? The sweet pepper has evolved. It's both the same species, but we have got two different morphotypes. One is sweet, one is hard, one is big fruit, another is a small slender fruits. Like that, this within a species, the relation. But there is easy flow of genes. They can be easily crossed. So this is, you should understand how the compatibility is there between the species, and that will be the source of genetic variation create macro level and micro evolutionary level. When alterations during evolution, there can happen that intrachromosomal changes, oligo or major gene changes can happen, or it can be, the polygenes or minor genes can be there, changes. That is okay, intrachromosome within a chromosome. This means maybe one or two gene changes, or polygenic changes, or minor major gene changes you can have. And then, of course, one gene or the major gene can change. You know the difference between the major and minor genes. Major gene is one gene will have big change, big effect. Whereas minor gene, small effect will be there. It's like polygenes only. Then the chromosomal changes with respect to their number and ploidy. Lot of variations you can find in chromosomal changes, right? All chromosomal operations, aneuploids, or even away from the diploids, all changes you can get during the evolution. Then intrachromosomal changes. If you look at the major gene changes, altered by mutations, one or few genes involved brings major, bigger, greater change. Example, non-shattering habits of cereals and dwarfing genes in wheat and rice. See, these examples we are taking, the evolution, the studies are available with us. The heading in cabbage and cauliflower, single stroke, it has happened. Although they are not different species, but they are botanical varieties, but morphologically they are different. Cabbage is different from cauliflower. Otherwise, both Brassica, oleracea only botanical varieties changing. So, but the big changes there. This is because of the single or a few gene changes involved, giving right to totally a different types of genotypes. You are terming them as a different crops. Major genes for disease resistance, and major gene, whenever it comes, it's a vertical resistance, which is often not stable because suddenly breaks. You don't have answer. That is a major gene. Then minor gene changes, many genes are involved, fine adjustment for the adaptation of the genotype in its immediate ecological habitat, controlled by polygenes or microgenes. Minor gene changes. Minor genes or polygenes render horizontal kind of resistance, whereas major gene, you have seen that vertical kind of resistance. Yes or no? Whereas here, the gradation is there. Major gene means it is resistant or susceptible. Minor genes means it is as the number of genes are more accumulated, level of resistance is changing. It's not resistant or not. It can be moderate resistance, it can be moderate susceptible, like that gradients can be there. So those changes you can get. Hutchinson in 1965 has stated that given the initial improvement conferred by the major genes, further progress, greater value may well follow from the selection in the polygenic variation process. Change, you can get it from the major gene, but subsequently, finer adjustment, more value you can get it from the changes in the polygenes, minor genes. Okay, so that is the whatever the chromosomal intrachromosomal changes said it, and then this is the chromosomal changes. In general, diploids better than the polyploids as far as breeding value is concerned, because the other than diploids, they're always having problems in the reproduction, their value also. Breeding structure of crop plant influences polypredation more than the selection process under domestication. It is breeding structure of the crop, that can. For example, gramineae, outcrossing easy, gene flow between the species to species easy, so polyploids are common. And the leguminaceae, it is restricted. Gene flow is not there from one plant to other plant, highly self-pollinated, and there will be fewer polyploids. Polyploids are rather not common in these legumes. So there's breeding structure, whether they're cross-pollinated or self-pollinated. Based on that, the ploidies, the cross-pollinated crop, this can sustain. I mean, they can sustain the ploidy changes, right? So that's happened. You can find the ploidy changes, the chromosomal changes you can find. However, role of polyploids in the evolution of superior crop varieties cannot be ruled out, especially in leafy vegetables and crops where the vegetative part is economic and the propagation method is asexual. So you cannot rule out. Of course, the majority of the crop plant, whatever you are getting, they are diploids only. Diploid breeding value of the diploids is much better, far better than the asexually propagated, or the ploidy level whenever you get other than diploids, they are always. But there are examples like your Vendi, the MP diploid, okra, MP diploid. You have got value, right? But that is rare. You consider the entire range of the crop plants existing on the universe. It is always the diploids having more breeding value. But certain cases, you cannot rule out this ploidy change in the course of evolution of certain crops or value of that crop that is asexually propagated crops, right? So that's what although the leafy vegetables said are some of the crops were asexually propagated, there the ploidy value is there. Polyploids have given. There can be a few exceptions also. So human selection and development of cultivars, yes, you understood what is the role of evolution, and that can help the plant breeders to take certain measures or how to go ahead. The evolution under domestication is a close counterpart of evolution in nature, right? As said by Mangelsdorff, 1961. That means you should know this evolution. Human selection is guided to improve the components of adoption, mainly the productivity and its attributes. Not many things you are looking at. Other things are happening in the nature by the course of evolution. Human activity remains confined to mostly below the species. We are not trying to create new species or something like that. It's only utilizing within species whatever variation is there. It is human activities remains confined to mostly below the species level during the evolutionary process. So natural selection, difficult to guide, right? Natural selection, because it's a long process. You don't know, you cannot predict what kind of pressure, natural selection pressure is going to happen this time. And natural selection, mutation, hybridization, and polyploidy. If all these things are directed to a specific goal, right? If you plant breeder, right, goals, I mean specific goals, can give excellent results and thus become a useful techniques of plant breeding. So we should know the evolutionary process and how this natural selection is difficult to guide. I understand, but still many times if you don't have time, no, you simply grow the crop, you grow the population. Natural selection, let it happen, because you are devoting your time. Breeder is devoting for some other schemes. Here you just go natural selection. It takes time. So it's like, the bulk breeding, if you look at it, will take more than 10, 12 years. So it's like a natural selection only. So there also mutation, hybridization, polyploidy, all these things, if they are directed to specific goals, it can give you excellent results, and thus becomes useful techniques in plant breeding. So that is what, the importance. And we have also discussed about, taking examples of cereals or other than vegetable crops, or counterparts where what is existing, it is, they are not very different from it. All depends on their structure, biological structure. That means whether they are self-pollinated or cross-pollinated. That will matter more than saying vegetable crops, cereals, or pulses, right? But whether they are self-pollinated, cross-pollinated, or cross-pollinated is very, very important, considering them as a group of plants for crop breeding. Goals of plant breeding. Plant breeding is a deliberate process. It destined for uh, definite goals of goals to bring about the improvement in crops in respect of the following things, like productive capacity, the yield you can increase, and then the quality consideration. Yield, the productive capacity, of course, to which comes your disease resistance, stability, everything stable. One, for disease resistance, the resistance to biotic, abiotics, whatever kind of this, but productive capacity, high yielding ability. Then the quality consideration is important. It's market value. Just getting higher yield is not sufficient. Especially this is important for vegetable crops. Market value, appearance, color, glossiness, high specific constituent content to catch the market. The brinjal, if you have got shiny fruits, people will buy. If the dull, any vegetable, if you take even tomatoes, so shiny fruits, the many of the vegetable crops, that will fetch you more. Glossiness, high specific constituent content. Maybe, of course, at present may not be there that much appreciation for these constituent contents, like the high vitamin C content varieties sold at higher price, but definitely future you can get. Of course, nutritive value, like the specific constituent content means it is nutritive value, protein, fat, minerals, vitamins, carbohydrates content. It's important quality. Then the palatability, fiber content, smoothness, texture. If the consumer should feel to eat it, that is very important. So those are the goals of plant breeding. And of course, this is resistance. Yes, productive capacity, we said it. Of course, disease resistance, like that, if you split to many components, it becomes disease resistance, safest and cheapest method of counteracting the diseases. Then adaptive ability, yes, it is different environments, insect resistance, abiotic stress resistance, drought tolerance, heat tolerance, cold tolerance, salt tolerance. So ultimately, to say, you are looking at any plant breeder, whether you are vegetable or any plant breeder, looking at productive capacity means yield higher by utilizing the whatever resources available. They're all agronomic practices you are defining. And of that, it should give the higher yield, then the quality, then disease resistance, adaptive ability, change in the environment or change in the season, the location, season, that your variety should give higher yield, and insect pest resistance, And abiotic stress resistance like drought tolerance, heat tolerance, cold tolerance, salt tolerance. All these are going to be the goals of plant breeding. Depending on the crop you have been given, we have to, you have to choose some of these. And of course, there's one more thing you can say: the suitability for new crop husbandry to suit to new kind of agronomy, such as multiple relay cropping system. Then your variety has to be different. You want to use this variety as an intercrop. Yeah, again, the definition or the area type is going to be different. Crop duration adjustment you have to look at. Crop canopy adjustment you have to look at. Root growth adjustment you have to look at. And then interaction of this your variety with other co-crops. This combination means it's infinite, the combinations. If this particular system is very prevailing in that particular location, then you have to start breeding, like the tomatoes or the chilies or something to grow in the early season of sugarcane fields. Like that, you can have variety suited differently. But by and large, all these requirements, productive ability, and then quality, then adaptability, disease resistance, insect pest resistance, and resistance to abiotic things. And of course, it is when you say the adaptability is also, and then the suitability for a new crop husbandry. This is very important, a new concept, because to sustain your farm income, you cannot rely on one crop. Intercrop you can go, or relay crop you can go. So all that, your variety had to be breed separately. All these objectives are rarely exclusive, rather than always mutually interlinked and desired simultaneously. So whatever, components with it, high productive means unless the variety is resistant to disease, it cannot have the high productivity. That means they are mutually related, mutually interlinked. It's resistant to some abiotic stresses means then only variety can be high yielder. Right? Adaptability. Unless it adapts to particular, you cannot give the height. So whatever the goals we have said, they are rarely exclusive. Maybe quality you can say, but again, quality, if you try to get it, yield reduces, that is also interlinked. So rarely they are exclusive. Rather, always they are mutually interlinked and desired simultaneously. You have to look for all these characters, many of these characters, at least few income at a time. So hence, they have to be tackled concurrently rather independent. However, in actual practice, that improvement in particular aspect is more desired. You cannot do it everything. Many times it is required, but you may not do it, may not be able to do it. But few of the list, whatever the objectives, reading goals were listed, that at least you can take it. So in actual practice, that improvement in particular aspect is more desired than in others. So it depends on the demand of that particular locality or the situation of the crop grown. Since the improvement in all these features of the plant is nonetheless a synergetic process. That means all this you cannot do it at a time. You can take step by step, or you can give importance for a few of these goals first and then look at the others like that. Breeders should consider these points before starting a program. So well-defined breeding objectives you should have must be matched with well-conceived blueprint. That means what is locally required, what is on demand. Only those you can keep it as objectives of breeding. Then that's first you should know what do you want to get, what are your breeding objectives. Then knowledge of following, whatever is listed here is very important. Gene action commanding the phenotypic expression, genetics, genetic diversity showing the range of heritable variation, whether the variability is there or not, right? Diversity is there or not, which is, the part of that only is heritable. How much part, how much is heritable? Variation is, diversity is required, but what the range of the diversity is, the heritable variation, right? Then that means heritable components you should know. Gene action, how many genes are involved, then only you can predict at least the amount of heritability and the environmental interaction. Then genetic system showing flow of variability, whether it's cross-pollinated, self-pollinated, whether it is incompatibility is there. All that genetic system showing flow of variability was. So many times, the general plant breeders, they know what about the plant breeding principles, but they do not know the crop? That's an advantage of these vegetable science students having. You know the crops very well because you have spent more time with these crops. You know what kind of system is prevailing, what is the evolutionary aspect prevailing in these crops, whether they are self-pollinated, cross-pollinated, or open cross-pollinated. What are the factors which are going to influence this extent of that? In addition, he is also supposed to know the gene to E interaction influence phenotypic stability, right? This knowledge, how at least a few studies you can do it, and it will help you to design your further breeding program. Then, of course, knowledge once is there, objectives are there, variability is there, heritable variability is there with you. Then you have to formulate the breeding procedures. So what breeding method you have to follow? Your objectives, your genetic knowledge of that crop, your genetic variation or the germplasm is there or not. Then you can formulate, depending on all this knowledge, you have to formulate the breeding procedure involved in different appropriate breeding methods, right? Whatever you read it and learn it in the textbooks and the classes, what is going to be applicable for that crop, depending on the situation, requirement. So breeding methods. So to all this, you should design to achieve the objectives what you have set, which are meaningful, and it is required for not for the self-interest. Some breeders they do it just for the sake of developing it. No, that should be required by people, end user, the farmers, right? So that is ultimately, what the breeder should consider, prepare himself. So then only will become a successful plant breeder. Useful. So with that, we are closing on the first chapter. Class.